Yes, hello everyone. We're going to get started here in the next couple, 2 or 3 minutes. I see we still have people coming in, so I'm going to give a couple minutes more to allow everybody a chance to get signed in here, and we will get started. Talk to you soon. Hello everyone, and welcome to another Flint & Walling virtual training event. My name is Dan Painter. I am the Product Training and Development Manager at Flint & Walling, and I'll be hosting today's broadcast. Today we're going to be talking about submersible motor testing using multimeters and megohmmeters. All right, just to kind of outline what we're going to do here is we're going to kind of go through a virtual testing of some submersible pump motors using multimeters, and then we're also going to talk about how to use a Megger and when to use a Megger. But all this is in an effort as a troubleshooter. You know, there's not a lot of repair, it doesn't seem, especially on fractional horsepower pumps these days. Not a lot of repairs done, mostly replacement. But I still think that there is merit to maybe understanding what caused the failure, you know, what might have been the root cause failure. And so that's what we're going to use these meters today for, is to test some submersible motors in our effort to determine what may have been the root cause failure. So we're going to start off, we're going to talk about multimeters first, and then we'll circle back on the Meggers a little later. But when talking about multimeters, obviously there's a couple of choices in the marketplace today. One, as you see on your screen, is an analog meter, and then right next to it is a digital. So whether it's an analog or a digital, irrespective, we can accomplish the same task, same goals with either meter. I actually as a lot of old timers, cut my teeth on that Simpson 372 there back in the day. When we do talk about the analog meters, on the other hand, just be aware that they do have an adjustable scale at the bottom, and that should be set prior to taking your measurements and looking at your values. So they've got the scale down there. And then they've also got a dial for zeroing out the meter. And that's a couple of things that were very, very common with analog type multimeters, is you had to adjust the scale and then zero the meter out each and every time. Whereas the digital meter, it's got auto ranging features to it, so there's no need to do either one of these, quite frankly. And obviously, we're in the digital age, and so obviously these digital meters are far more popular and prominent today than the analogs. Irrespective of the meter, when using the meter, you want to, prior to using the meter, you want to make sure of its functionality. And so to do that, you cross your probes. When you cross your probes, like pictured on the screen there, your meter ought to read what is referred to as infinity. And infinity can be displayed one of two ways, either an OL, like you see up there on the left, or simply a 1. But be sure the meter has functionality prior to using it, because you need to make sure that the information you're getting is accurate. And obviously, kind of a CYA comment here, but obviously there should be no power going to the motor. If you're testing the drop cable, cut the power off to the pressure switch, but you should have no power going to your pump motor or your drop cable when performing any of these tests, because these meters will operate fine and they'll measure that resistance without any power being applied at all. So shut the power off. Make sure you cut the power. All right, here we go. Again, when I do these web conferences, I'm talking to people undoubtedly from various parts of the country. And that said, submersible pumps, in various parts of the country, there's various types of pumps sold. 2-wire, like you see on the screen, very popular out east. In fact, as you go east to the Mississippi, 2-wire motors on submersible pumps are very popular, and that Mississippi seems to be, at least in my opinion, a bit of a dividing line, because as you go west out of that Mississippi River, then you start to get into more 3-wire motors. And so anyway, let's just talk about them both here real quick. 2-wire motors actually got 3 leads coming off of it. There'll be 2 black wires. We'll simply refer to those as lead A and lead B. And obviously there's going to be your ground wire, your green ground wire. So in identifying motor cables on a 2-wire motor, pretty easy. Again, just 2 black leads and a green ground wire. When we move to the 3-wire motor, on the other hand, and again, these are very, very popular out west. I know down in Texas, a lot of 3-wire motor, pump motors sold down there. So let's look at the 3-wire motor and identify these leads. The green will always be the ground, obviously. But then, unlike the 2-wire motor, where we simply had 2 black leads, on the 3-wire motor, in addition to the green ground, you have a red, black, and yellow. So let's identify what those are. The yellow is going to be your common. So the yellow wire, and this is pretty standard throughout the pump industry with various motor manufacturers. And much of what I'm talking about today is applied across the industry in as much as testing submersible motors. Your black is your run winding, and then the red one will be your start winding. All right. So with the 3-wire motor, you're going to have 4 leads coming off the motor leads, and green ground, yellow common, black run, and red is the start winding. This is important if you're in an area of 3-wire motors. Hopefully there'll be a couple of good, strong takeaways from today's presentation. When using a multimeter, there's a variety of things that we can test for. We can determine whether a motor is good. We can also determine whether it's got a ground or whether it's shorted. A variety of things can be determined with the use of a multimeter. We're going to start off and we're going to talk about how do we test a motor to determine whether it is grounded or not. So with that, we'll form a little chart here, and we're going to try to determine whether a motor is grounded or not. So how do we measure, how do we measure that? Well, to determine a ground, you will take each lead to ground. So, and I'm going to show you this in a second. On a 2-wire motor, obviously, you've got 2 black leads to ground. On a 3, you're going to have the red, yellow, black to ground. But this is the only time that we're going to take any of those leads and run them and test them across to ground, okay? Only when you're checking for a ground do you need to use a ground. So, what that basically means is on this 2-wire, we're going to take a black wire to ground, and we're going to take the other black wire to ground. We're going to take 2 readings, each one of those leads to ground. Same with the 3-wire. With the 3-wire, we're going to go yellow to ground, black to ground, red to ground. Now, in so doing this, all right, when you take your leads to ground, if you get no resistance, none, you still have an infinity reading in your multimeter, then take confidence that that motor is not grounded. I'm not saying it's good. I am saying it's not grounded. And so if you get no resistance at all by taking those leads to your ground, then there would be no ground. On the other hand, if you get resistance, that motor's grounded. The guy says, well, wait a minute, how much resistance? Any resistance. So keep that in mind. Any resistance, large or small, when you're checking a lead to the ground wire and you get resistance, you have a ground. So this is pretty black and white test to be able to run. It either is going to have resistance or there'll be no resistance. And it's, like I said, it's black and white. So I was doing a contractor meeting a couple of years ago, and this was the topic. And one of the contractors had come up to me who was going to attend my little training seminar, and he made a comment to me I was at an open house, and he come up to the little table where we had our displays. Mr. Painter, he said, I pulled a 3-wire motor out last week, and it was grounded on all 3 legs. That's what he said. He said it was grounded on all 3 legs. And he acted a bit surprised about that. But the truth of the matter is, I wasn't too surprised, because that's more the rule rather than the exception. So in most cases, if you're getting resistance on any lead, you'll probably get them on all of them. Again, that's what you're looking for when it comes to ground. Yeah, I don't know if there's going to be a day may not have to mention this anymore. I don't know how, if you test an old motor, in the early days of submersible pumps, number one, there were no 2-wire motors. They were all 3-wire motors. And number 2, none of them had ground wire. So it was up to you, the installer, the pump installer, to ground that pump and motor assembly. They did not have a ground wire on them. But I don't know how many of those motors may still be out there today, because we're talking about, probably 3 or 4 decades now. But if you happen to have an old motor that you pull out and it doesn't have a green ground wire on it, we got to find a ground in order to test it. So a lot of water well drillers, they're very familiar with this image on the left-hand side, where if you've got a steel cased well, you can take that probe and run it up and down against that steel casing and get yourself a nice solid ground there. But you got to have a ground if you're going to test any of those leads to determine whether they're grounded or not. So here's one way of doing it. Another way, if the motor and the pump and motor is out of the well, you can actually use the side shell of the motor as a way of grounding your probe so that you can determine a ground. But again, when we're talking about grounds, we're talking about taking each of the leads to the green ground wire, each of them. If there's no resistance, the motor is not grounded. And if there's any resistance at all, you have a grounded motor. And so in my way of thinking, that's a pretty easy test to run, and the results are pretty conclusive, pretty black and white. All right, so we talked about a ground. What about some of these other things that we can test a 4-inch submersible motor with a multimeter, such as open windings or a shorted motor, or one up there is called mixed leads. All right, so let's talk about that for just a second. Again, we're just using the multimeter right now. So we've got a problem indicated that we want to determine if a motor has a short, if it perhaps has an open winding, or if, in fact, although this is pretty rare, mixed leads down there at the bottom. When you do these tests, you're going to take each lead to lead, all right, each lead to lead. And as I mentioned before, the only time that green ground wire comes into play is if we're checking the motor for ground. Short of that, no pun intended, we're going to measure each lead to lead, all right? So when doing that, your multimeter is going to show some resistance values in ohms, all right? It's going to show you some values in ohms. And based on what those values are, you're going to be able to determine any of these problems, or if, in fact, the motor's still good, all right? So when it comes to these values, you know, somebody say, well, what are you talking about, these values? You know, what should they be? Well, a couple of things. I think everybody that manufactures a 4-inch submersible pump motor, and I know you've got Faradyne, Franklin, us, and Grundfos pretty much. I'm pretty sure we all put out manuals. This on your screen is a motor application guide. By the way, I've also attached this motor application guide to your dashboard. So if you look down on your dashboard, there should be a tab down there called Handouts. And I've put a couple of PDFs out there for you. This motor application guide is another. And one that marketing always wants me to bring up is the fact there's also a survey out there. So if you'd like to give us some input on how we're doing and what we can do better, feel free to fill that out as well. But anyway, in these motor application guides, Franklin puts out an AIM manual. Grundfos has their motor manual. I'm pretty sure everybody does that has a manual. That's where you'll find these values. All right, that's where you'll find these values. Now, inside our motor application guide is this table here. So let's just look at this table once, and whether it's this Flint & Walling table, and obviously this is going to be geared at a Flint & Walling submersible motor, you'll find a table similar to this in anybody else's motor guide. So let's just look at this guide real quick. Over on the far left-hand side, something we've already talked about is we've got to determine what are we looking for. Is it a 2-wire motor or is it a 3-wire motor? And right next to that is the horsepower. So you know, is it a fractional? Is it a horse and a half, 2? So there's your motor type and your motor horsepower. Now, if you scroll across that table, you'll come over here to where it says, I got to move my dashboard out of the way because it's blocking my right-hand side of the screen, where it says winding resistance, and those are all going to be listed in ohms there. So right here they are. There's your values, all right? There's your values. They're published. And I would have to assume every motor manufacturer publishes these values. So let's see, I got to get my thing to advance here. There we go. So let's just, for sake of discussion, let's take a 3-wire motor, Let's just say we're going to test a 3-wire motor. And now we got to determine, okay, so what horsepower 3-wire motor are we going to test? Half, 3/4? Let's make it a 1.5 horse, all right? So what I'm trying to show you here is that when you know your motor type and you know your horsepower, there's your values right across there. You've got an M value, and that should be coming in at 1.7 to 2.2. And you have what's called an A value coming in at 7.8 to 9.6. If you look closely, there's a little table down at the bottom of that chart that tells you what that M and that A represent. So, for example, the M represents, down here on the bottom right, represents your yellow to black, all right, your yellow to black, and that's the M value. So that's should come in at 1.7 to 2.2, that yellow to black. The A value is yellow to red, so it's common to start, common to run, yellow to black, yellow to red, and your values there are 7.8 to 9.6. So again, these values are not, they're published, and so therefore they're accessible. Okay, so let's go ahead. Now, again, if it's a two-wire motor, all right, if it's a two-wire motor, you look up there at the top, you're only going to have one set of values there, right? Just one set, because you're going to go black to black, and that's it. So you're only going to have one set of values, but they are published up there. All right, so let's go ahead and let's kind of go through a virtual test of a motor. The takeaways. I mentioned there was a couple of takeaways. Hopefully this will be one of them, especially if you're in a three-wire market, okay? So here's a takeaway, and this is general knowledge. This is not exclusive to F&W. This is pretty much across the board for motors. When you do check that yellow to black, which we talked about being that M value there, that low resistance of 1.7 to 2.2, when you do check that, that should be the lowest of the resistance that your multimeter will show. And then we go to the A value, which was yellow to red. All right. So when you put your multimeter on yellow to red, the resistance there is higher, obviously. So we're going to call that the intermediate value. Now, in these manuals, these are the only two values you're going to get for a three-wire motor. These are the only two. You do not get the run and the start windings together down here. But when you do cross those leads, run red and black, that should represent the highest of the values. So there you go. You've got your lowest, your intermediate, and your highest. And again, the only values you'll have for comparison's sake are going to be the low and the intermediate, as pictured in that little red box there towards the center of the screen. Again, those are the only values that will be published. All right, so if the yellow to black is published and the yellow to red is published, what in the world then should the red to black be? They start to run windings. I mean, you know, what should that be? We know it should be higher than the other two based on the low, intermediate, and highest value, but how high is too high? You know, what is the answer there? And here's a good takeaway for you. To determine what that highest value should be when using a multimeter, it's pretty easy math, folks. You take that lowest value, whatever those come in, and you take the highest value, or I'm sorry, the intermediate value, you add those together, that ought to give you awfully close, maybe not right dead spot on, but awfully doggone close to what the highest value should be when you do run that red-black wire test there. So just a pretty basic math thing. Okay. Let's go ahead and let's do some testing now. We've got this horse and a half motor, three-wire. We've got it up on the workbench here. Let's just see what's wrong with it. So we're going to take our multimeter, and we're going to, the very first thing we're going to do is we're going to take an actual reading off our yellow and black, our common and run winding. So we'll put the probe on there, and when we do, I get a resistance value. If you look at the left, I get a resistance value of 2 ohms on my multimeter. Well, when I look at the range, it should come in between 1.7 and 2.2. So, you know, I'd give that a good grade. That's right where it needs to be. So now I'm going to move down to the common and the start windings, the yellow and the red, which is my A value that's published as well. And when I run that, I come up with 8 ohms. All right. Again, 7.8 to 9.6 is what that range is, and that 8's falling right in there. So I would look at that and say, well, so far, so good. Now, based on what we talked about in the previous slide, I don't have a comparison to determine the value of my the highest value here. So, you know, if we use that little math, you know, I should be coming in based on what we've got on the screen so far. I should be coming in somewhere around 10 ohms. And so when I do the test, and there it is. It doesn't necessarily have to be right spot on, but it ought to be awfully close and make sense. And so I'm showing, 10.1 down there on my run and start windings together. And so based on what we just tested here, I'd say this was a good motor because everything that we tested came through as within range. And given the fact if the motor's not grounded, right, and that's a different test we're doing now, but that would be a good motor. So let's go do another test. And the other thing I tried to do, and I basically do this for my own benefit more so than anybody else, I try to come up with ways that I can remember stuff, because the old mind, thank God they got Prevagen out there, I guess. But I try to come up with ways I can remember things, and in so doing, if it works, I'll share them with you. And so we're going to see that here in a second. So we're doing another test, all right? Common and yellow, common and run windings, yellow and black. We're going to run right down through this again. I'm coming up with 1.8. And again, I look at the range and I have no issue with that. It's 1.7 to 2.2. It's within that range. I give it a good grade. I'm going to drop down and I'm going to do the second set of leads. I'm going to go to the yellow and the red, and I'm going to come up with, that's not good. I'm coming up with 1.7 ohms. And that's supposed to be 7.8 to 9.6. So that test right there failed. I'm not within range. I'm not showing the resistance I should be. So that one fails. Now let me tell you something. Anytime one of these two top fail that are published, the yellow and the black and the yellow and the red, anytime one of those two are failed, I guarantee you the bottom one will always be skewed and it'll be failed too. And so you've got a couple of bad readings here, right? The one that we're going to dial in on is the one that's published. The one that's published says it should be 7.8 to 9.6, and we're coming in at 1.7. So what's that mean? That means we are coming in lower than the specified value. Yes, lower than the specified value, right? Lower. Now, when the resistance values are lower, think of it as shorter, all right? So if the resistance values are low, you have a short. If you want to mow the grass shorter, you have to lower the mower, right? So that's how I've always remembered that if I get a low resistance reading, it's coming in short. It's coming in short, all right? So that's how I remember that. Corny as it may be, it's worked for me. But let's go back to our test that we just ran. If it's within specs, fine, everything's good. But if it comes in lower than specified, that indicates a short. Now, we talked early on when we started this session that we would, as a troubleshooter, sometimes it's nice to determine, root cause failure. Well, in this case, we've determined that we've got a shorted motor. But if you look at these tests that we ran, the bottom one failed and the middle one failed. Those two failed right there. The black wire worked well when it was paired with the yellow. The yellow worked well when it was paired with the black. Neither one worked well when they were paired with that red wire. And so you can count on the fact that you have a short in your red wire in your start winding. All right, that's the one that's shorted right there. Okay, it's the common, it's the fly in the ointment there. It's the one commonality between those two red boxes that show a failure there. That's the one common player there. All right, let's do it again. We're going to start off at the top. We're going to do this again. The point here is if they come in lower, it's a short. So let's do it again. Here we go. Woo, failed already. I did a yellow and black test, and I'm coming up with 8 ohms over here on my multimeter. That's not within range, obviously. And the fact is, it's higher than the specified values. So I'm going to drop down, and I'm going to check the yellow and the red windings of the start winding together. I'm going to check those. And when I throw those up there, put those probes on those two leads, I'm coming up with 9.4. Well, that works okay because the A value there, that intermediate value with the yellow and the red, should be 7.8 to 9.6, and I'm coming in at 9.4. I'm going to give that one a passing grade. Now, I mentioned in the previous slide, I'll mention it again. If one of these two top ones fail, the bottom one always will. You'll never get a right reading on there. All right? So, but if we look at what's going on with our readings, I'm trying to get these slides to advance. There we go. I'm coming in higher than specified. All right? Higher. This is how I remembered. Walk out back. I look into the open skies, right? It's just nothing but open skies. And so anytime, this is just my way of remembering, folks. Anytime the resistance values are coming in higher than specified, that indicates an open winding, just like an open sky. It's an open winding. And just like what we did to determine which wire was the culprit for the short, we can do the same thing again with the test that we just ran. The bottom one failed and the top one failed. So can you determine maybe which wire has an open winding? Well, the yellow and the red work well together. They don't work either one when they're paired with the black. And so when that reading come in open winding, I know that it's in the black run winding. Okay, so that's where the open winding would be. And again, just kind of understanding these resistance values allows you to get right to a root cause and determine what was the root cause for the failure. So open windings, again, anything that comes in within the specified range, that's always a good thing. But in this case, if they come in higher than the specified, it's going to be the indication of an open winding. All right. We're going to run one more test here, and then we're going to switch to Meggers, and I see I'm about at the bottom of the hour. So let's run one more test here, see what we come up with. We're still using that 1.5-horse, 3-wire motor, still has these same published values here. So when I do the first test, obviously, boom, that's no good again. I got 8 ohms up there, and I should be 1.7 to 2.2. So I'm coming in higher, right? We talked about that just a second ago. Now I'm coming in higher. So I'm going to move on down, and I'm going to check the common and the start windings, my yellow and red wire. I'm going to put my ohm meter on there, and I come up with 5.3. All right, well, if I look at the A value for the yellow and red, that should be 7.8 to 9.6. So in this case, I'm actually coming in lower than the specified value, lower. And again, just forget that bottom one anytime one of the top two fail. But here's the last of the things that we can determine with a multimeter. In this case, I've got resistance values that are coming in both higher and lower than the published values. So with that all said, when they're coming in higher and lower, it's mixed. It's mixed leads. That's what we're going to call that. It doesn't know whether it should be higher or lower, but it picks both. It's mixed leads, all right? Now, when we talk about mixed leads, and I mentioned early on that this is more of a much more rare occurrence than a short, a ground, or an open winding. But when you have mixed leads, I suppose there's a possibility when that motor was manufactured, if they didn't orient the lead socket properly, and then you put the motor lead on it, and the wires aren't lined up appropriately, that could be a result of a mixed lead and give you those higher and lower results with your multimeter. I don't know. I mean, I'd tell you that could never happen at F&W because there's way too many tests that are done on that motor while it's being manufactured, and at the end of the line, it would never pass. So it would never get out the door. And I really don't think that this is a common issue here with the lead socket. I think where it's more likely going to take place is at the splice. And I think most of you probably could agree with that. It's at the splice. Sometimes these, use an old drop cable, it's hard to even tell the colors of them anymore. But if you get your splice wrong and you don't have the wire spliced properly, expect those kind of readings on your multimeter. You're going to get high and you're going to get low resistance readings. So I would say that if you do get those, I'd go to the splice first. That'd be the first place I'd go versus that lead socket in the motor, and especially if the motor's been in there. Well, who knows? All right, so when they come in both higher and lower, that's going to be referred to as mixed leads. All right, so a couple of takeaways that I hope you will take away with this multimeter. Anytime we're coming in within specified range, that's always a good thing. Anytime we're within specified range. If we come in lower than that, lower than specified, it's a short. If we come in higher than that, it's open windings. And if we come in both higher and lower, it's mixed leads. All right, so that's one takeaway. Low is short, high is open, and both are mixed. The other takeaway was that little math equation. To be straight honest with you, and this is an opinion, I really believe I could go out with a multimeter, test any given motor, and not have those published values and still determine whether that motor is good or not, because I understand what this over here means, all right, on the right-hand side. So if that makes sense, when I'm all done testing, there's a good chance that motor is, going to be fine. So those two takeaways. All right, we're going to switch gears. We're coming down to a few minutes left here. And I want to talk about another piece of instrument that's not as common as a multimeter. A lot of contractors don't have these megohmmeters, all right, Meggers. What a Megger will do is it's going to measure what we call insulation resistance. And that's the one thing a Megger will do that a multimeter really is not the right tool for it. So it's going to test the insulation resistance. So when we look at the difference between the two, your digital multimeter, what's that thing put out? Like 9 volts. It's got a 9-volt battery in it, okay? So, you can put your fingers on the probes and everything else, no big deal. But when you're using a megohmmeter, a lot more caution is going to need to be taken place, because what a megohmmeter is going to do, it's really going to stress. It's going to stress that wire and that insulation to give you a good indication of the condition. And so if you look here, you want to use caution. It's putting out some voltage that could hurt you. So, or it's definitely going to give you a nice sting. So be cautious when using a megohmmeter. The other thing is that it measures in a megohm, all right? So it's going to measure in megohms. 1 megohm, just one, is equivalent to 1,000,000 ohms. And so a Megger is a much deeper type of test. Again, it's going to really exploit the insulation on not just the coating on the wire and the motor leads, but the windings in a submersible motor, the stator windings. That copper wire has a thin film of insulation on it as well. And so we want to make sure that hasn't degraded over time. And a megohmmeter will allow us to do that. Again, it's going to really exploit the insulation around your drop cable. Okay, so nicks, thin insulation, cracks, pinholes. Again, some of this just is going to degrade over time, including the copper winding in the stator. All right, and this megohmmeter is going to allow us to determine the condition of all these things. So, I get asked this occasionally, that copper wire that you talked about. Is copper wire and magnet wire the same? Everybody looks at motors and say, well, it's got copper windings. Well, really it's a magnet, okay? So both use a copper conductor. However, magnet copper wire has a thin, high heat absorbing special coating or insulation. That's what I just mentioned a minute ago, like an enamel or a varnish. This insulation protects the windings from contamination. We will encapsulate these motors so that the windings are encapsulated in what almost is like an epoxy to eliminate vibration that could prematurely wear that insulation off. So there's a lot of work done on the inside of a motor to tend to these copper windings that are in there. I throw this up to my own guys every once in a while, you know. My dad used to tell me, because I asked a lot of questions when I was young, he thought I asked way too many questions. And he said to me one day, he says, "You ask a lot of questions. Let me ask you one." I said, "What's that, Dad?" He says, "How's a brown cow eat green grass and produce white milk?" I said, I have no idea. He said, "You're absolutely right. You don't. So you don't need to know everything." So this is something that comes up, and I kind of throw it up here. This is understanding insulation testing doesn't require you to delve into mathematics and all that, but there's this thing called Ohm's law, right? And do you need to know Ohm's law? Well, when spelled out, what it means is this: voltage will equal current times resistance, or another way of saying that is voltage equals amps times volts, or I'm sorry, amps times ohms. And let's see, move to this next slide here. So, all right, here we go. Ohm's law, right? Here's how I explain it. Other people do it this way too, I think. Ohm's law can be better understood by comparing it to water flow. Well, that's something we all are familiar with. All right, so we take this copper wire and we're going to insulate that in the insulation that goes around that wire. All right. So down here we've got a piece of PVC pipe. When we put a pump on the end of that pump is going to push water through that pipe, right? That's what happens. So when you put your megohmmeter on that drop cable, we're not pumping water, we're pumping current, a lot of voltage. That's kind of the same thing. We're pushing, that's why we're using a megohmmeter, is to push that additional voltage through that insulated wire. With the case of a pump and a piece of water pipe, you know, we've all talked about the fact that we can experience friction, right? As that water travels through the inside diameters of that pipe, it rubs against the inside walls and creates friction. With the megohmmeter, what we're going to measure is resistance. So there's a lot of commonality here between water flow and Ohm's law. Because if you get a leak in that water line, you get a leak somewhere, obviously you're going to lose pressure, you're going to waste water, etc. And what that megohmmeter will do is it'll tell you whether you've got a potential or if you've got, in fact, a pinhole or a crack in that insulation, whereas you can also have a situation where you're either going to go to short or going to go to ground. So as a troubleshooter, applying high volts, which is what we're doing with that megohmmeter, we're doing that so that we can, you know, really stress this insulation out. All right, so now what do we do with that? What do we do with this information? And one of the handouts that I have attached to the dashboard is a resistance values chart. It's pretty generic, meaning I think if you compare it with a Franklin or a Faraday, you're going to find, you know, these to be very, very comparable. So, you know, people ask me, we talked about the values early on with the multimeter, you know, what should the values be? Well, here that question can come up again. You know, what should the values be? Well, that's going to be dependent on a few things. One, is it a new motor or is it a used motor? And two, is it out of the well or is it in the well? If it's out of the well, out of the box, brand new motor, hadn't been installed yet, you put a Meggers on there, and when you use a Meggers, you're going to go lead to ground, lead to ground, lead to ground, lead to ground. You should be reading 20 megohms or more. With a used motor, that reading should be 10 megohms or more. And again, this is a fairly standard within the industry. But here's the thing you need to know. If those values are coming in below that, don't install them. Don't install them. You've either got a problem that is current or is about to happen. So if those megohm values come in lower than what's on the screen, don't install that. And that's out of the well. Now, these change considerably when we're testing in the well, because when we're testing in the well, we're testing all that drop cable and that motor lead and across those splice right down into the motor windings. So if it's new motor and it's in the well, we want 2 megohms or more. And if it's a used motor in the well, that'll be a half a megohm or more. So those are a couple standards. And I put this in a chart. I don't know if that's the next slide or not. But again, anytime these values are coming in less than that, don't install it. This is of note. Most motors of all horsepower, voltage, and phase will have very, very similar insulation resistance values. So that's something to note. And obviously, we're using a megohmmeter. It's throwing out a lot more voltage. This is not this is a non-destructive voltage to the motor. However, not so much us. So if you're testing a motor and it isn't in the well and you've got it on a bench somewhere, make sure that it's on a non-conductive surface when you're testing it out of a well. So here's a couple of charts that I've got that as a part of your handout here. On the left-hand side is what we call our motor application guide. And that table that I showed you early on that showed the various resistance values for the type and horsepower of motors are all published in this guide, along with a whole lot of other information, kind of similar to an AIM manual in some ways. And then I put this chart together, for our field tech people, just so they had a quick reference when we're talking about using a megohmmeter. And so at the top, you've got whether it's in the well or out of the well, and then you've got new motor, used motor, and then those orangish areas there is areas where we don't want to put that motor back in the well. Well, folks, I think I've talked it all out. We just talked about how to use multimeters and Meggers. Again, Meggers are not a common tool that I find a lot of contractors have. I think anybody that's selling variable frequency drives probably ought to invest in a megohmmeter, because those things can throw a lot of voltage, and that's a great tool to have if you're troubleshooting variable frequency drives as well. So I guess with all that said, don't forget the handouts that are attached. Again, there's a survey there. I appreciate you all attending today. We're running these all the way through March every week. And so with that said, everybody stay safe and hope to talk to you very soon. Thank you very much. This training has now concluded.